7 Brief Lessons on Physics, by Carlo Rovelli. Introduction. Imagine for a moment, a young man, not much older than you are now. He spent the last year doing, well, not much of anything. He's dropped out of his school in Germany, unable to stand the rigid discipline, and has joined his family in the quiet, sun-drenched town of Pavia, Italy. He isn't enrolled in the local university, but he attends a few lectures now and then, just for the pleasure of it. He spends his days reading philosophy, wandering, and wasting time. His father, an engineer, is busy installing the first electrical power plants in the region, a symbol of the new century's industrial roar. But his son, Albert Einstein, is simply loafing. And it is in this period of aimless wandering that the seeds of a revolution are quietly sown. Because, as the author of our book today reminds us, you don't get anywhere by not wasting time, something, unfortunately, which the parents of teenagers tend frequently to forget. That young man would go on to completely dismantle and rebuild our understanding of reality. And the book we're exploring today, 7 Brief Lessons on Physics, is our invitation into that new reality. Its author, Carlo Rovelli, is a brilliant theoretical physicist himself, currently leading a quantum gravity research group in France. But he is also a master storyteller. He wrote these lessons for people who know little or nothing about modern science. And the world responded. This slim, elegant book became an instant #1 bestseller in Italy and has been translated into dozens of languages, captivating millions of readers who never thought they could understand, let alone love, physics. Why? Because Rovelli doesn't just give us facts. He gives us a sense of awe. He peels back the veil of our everyday experience to show us the staggering, beautiful, and deeply strange world that lies just beneath the surface. So, here is my promise to you. Stick with me for this journey, and you will walk away with more than just a few interesting ideas. You will see the universe, the stars in the sky, the passage of time, the very space you're in, not as a fixed and boring stage, but as a dynamic, shimmering, and unfinished story. And most importantly, you will see your own place within that story in a way you never have before. Let's begin. Book summary. Our story begins with that young man Einstein, after his year of loafing was over. He had immersed himself in physics, and in 1905, he sent 3 papers to a prestigious scientific journal. Each one was a masterpiece. One proved that atoms really exist. Another laid the foundation for a bizarre new science called quantum mechanics. And the third introduced his first theory of relativity, the one that revealed the strange fact that time doesn't pass the same for everyone. A twin who travels at great speed will return younger than the one who stayed home. Overnight, Einstein became a star. But something bothered him. His new theory of relativity didn't align with our understanding of gravity. For over 200 years, everyone had accepted Isaac Newton's picture of the universe. Newton imagined space as a giant, empty box, a fixed stage where objects moved in straight lines unless a force acted on them. Gravity, he said, was a mysterious force, reaching across the void to pull things toward each other. But Newton himself was deeply troubled by how this invisible force could work without anything connecting the objects. Einstein obsessed over this problem for 10 long years. 10 years of false starts, dead ends, brilliant flashes of insight, and crushing confusion. Finally, in 1915, he published his solution. A new theory of gravity he called the general theory of relativity. The great physicist Lev Landau would later call it the most beautiful of theories. And the central idea is one of breathtaking simplicity. Einstein had a stroke of genius. He realized that the gravitational field isn't something that exists in space. The gravitational field is space itself. Think about it this way. Imagine a large, stretched-out rubber sheet. If you place a heavy bowling ball in the center, What happens? The sheet curves and dips down. Now, if you roll a small marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball, spiraling around it. That's what's happening in our solar system. The sun is the bowling ball. It's so massive that it bends the fabric of space-time around it. And the Earth, like that marble, isn't being pulled by a mysterious force. It's simply following the curve. It's moving in a straight line through a curved world. We are not living in a rigid, invisible box. We are immersed in a gigantic, flexible snail shell that can undulate, flex, and twist. Planets orbit the sun and things fall to the ground simply because space itself is curved. This one, beautiful idea unlocked a cascade of predictions that sounded like the ravings of a madman, but one by one, they all turned out to be true. The theory predicted that not only space, but time itself, can be bent. Time passes more slowly closer to a massive object. This has been measured. A person living at sea level ages just a tiny bit slower than their twin living in the mountains. GPS satellites have to account for this effect, or their calculations would be off by miles every single day. It predicted that when a truly massive star dies, it can collapse under its own weight and bend space so severely that it punches a hole right through it, creating an abyss from which nothing, not even light, can escape. These are the famous black holes. When Rovelli was a student, they were just a wild, esoteric prediction. Today, astronomers have observed hundreds of them. And perhaps most stunningly, Einstein's equation showed that the entire fabric of space cannot stand still. It must be expanding. This implied that the universe must have begun from a single, tiny, incredibly hot and dense point that exploded outwards. We call it the Big Bang. And in the 1960s, scientists discovered the faint, leftover heat from that initial explosion, a cosmic background radiation that fills all of space, confirming the prediction. This is the world of general relativity. A world where universes explode, space collapses into bottomless holes, and the fabric of the cosmos ripples and sways like the surface of the sea. It is a masterpiece, a coherent and stunning vision of the universe on the grandest scale. But it's only half the story. At the very same time Einstein was perfecting his vision of the cosmos, another group of brilliant young physicists, led by the Dane Niels Bohr, was exploring a world that was, in every way, its opposite. They were looking not at the vastness of space, but at its tiniest components, the atoms and the particles within them. And what they found would shatter our conception of reality itself. This new science is called quantum mechanics. And where relativity is a compact, elegant gem conceived by a single mind, quantum theory is a sprawling, mysterious, and profoundly strange construction that still baffles us a century later. It all began in the year 1900, when the German physicist Max Planck was trying to solve a problem about heat. He came up with a clever trick. He imagined that energy wasn't a smooth, continuous flow, like water from a tap. Instead, he pictured it as being delivered in tiny, discrete packets, or lumps, which he called quanta. This mathematical trick worked perfectly, but it made no physical sense. 5 years later, it was Einstein again who realized these quanta were not just a trick. They were real. He showed that light itself is made of these little packets, these particles of light we now call photons. This was the true birth of quantum theory. But then, the theory took on a life of its own, going in a direction that its own parent, Einstein, could never accept. A young German genius named Werner Heisenberg took the core idea and pushed it to its terrifying conclusion. He imagined that electrons don't really exist in the way we think of things existing. An electron doesn't have a definite position until it interacts with something else. When it's not being observed or measured, it's not in any one place at all. It exists as a cloud of probability. It only materializes in a specific location, at random, when it collides with something else. Think about that. The fundamental building blocks of our world are not solid little pebbles. They are ephemeral, ghostly things that only become real through interaction. Reality, at its most basic level, is not a set of things, but a set of relationships. As Rovelli beautifully puts it, it's as if God had not designed reality with a heavy, solid line, but had just dotted it with a faint outline. And there's more. These quantum leaps are not predictable. We can never know for certain where an electron will appear. All we can do is calculate the probability that it will show up here or there. This introduction of pure chance into the heart of physics was something Einstein could never stomach. He famously grumbled, "God does not play dice." For years, he and Niels Bohr engaged in a profound debate. Einstein would devise clever thought experiments to show the absurdity of the new theory. "Imagine a box filled with light," he'd begin. And each time, Bohr would patiently find the answer, showing how the quantum world, as strange as it was, remained consistent. In the end, Einstein had to admit the theory worked, but he remained convinced that there must be a deeper, more sensible reality hidden beneath it. When Bohr died years later, a photograph was taken of the blackboard in his study. On it was a drawing. It was the light-filled box from Einstein's thought experiment. To the very end, he was still wrestling with the mystery. And that mystery remains. We are now standing with two pillars of 20th century physics. One is general relativity, Einstein's flawless theory of the very large, of planets, stars, galaxies, and the expanding cosmos. The other is quantum mechanics, the wildly successful but deeply strange theory of the very small, of atoms, particles, and the probabilistic dance that underpins all of chemistry and modern technology. Both theories work remarkably well. And yet, they cannot both be right. At least, not in their current form. Because they contradict each other. This is the great paradox at the heart of modern physics. In the world of general relativity, space is a smooth, continuous fabric that curves and bends gracefully. In the world of quantum mechanics, everything is granular, jumpy, and probabilistic, taking place on a fixed, flat stage. The two theories speak completely different languages. A student attending lectures on both in the same day might think their professors hadn't spoken to each other in a century. And this is where the true adventure of physics is happening today. In the vanguard, beyond the borders of known territory, scientists like Carlo Rovelli are trying to solve this puzzle. They are searching for a single theory, a theory of quantum gravity, that can unite these two conflicting pillars and give us a single, coherent vision of the world. One of the most promising paths in this search is a theory called loop quantum gravity, a field where Rovelli himself is a pioneer. The core idea is, once again, astonishingly simple. It tries to take both of our great theories seriously. General relativity taught us that space is a dynamic entity that can be stretched and twisted. Quantum mechanics taught us that fields like this are made of quanta, or discrete grains. What happens if you apply the quantum idea to space itself? The immediate conclusion is that space is not continuous. It is not infinitely divisible. It must be made up of tiny, indivisible grains, or atoms of space. These grains are incredibly small, a billion times smaller than the smallest atomic nucleus. In this theory, these atoms of space are called loops, and they are linked together in a network, weaving the very texture of space like the rings in a cosmic coat of chainmail. So where are these quanta of space? The answer is nowhere. They aren't in space. They are space. Space is created by the relationships between them. The illusion of a smooth, continuous world around us is just a result of our blurry, macroscopic view. It's like looking at a calm alpine lake. From a distance, it seems perfectly smooth and still. But we know it's actually made of a frantic, chaotic dance of countless tiny water molecules. So too is the fabric of space-time. But the most radical consequence of this theory has to do with time. Just as the idea of a smooth, continuous space disappears, so too does the idea of a universal, flowing time. The fundamental equations of the theory don't have a variable for time. This doesn't mean everything is frozen. It means change is everywhere, but it doesn't happen to the beat of a single cosmic drum. At the fundamental level, there is no master clock. Each process dances to its own rhythm. Time is not a river that carries the world along with it. Time is born from the relationships between the quantum events themselves. This radical idea might even change our understanding of the Big Bang. If space has a minimum possible size, then the universe couldn't have been compressed into an infinitely small point. The equations of loop theory suggest that our Big Bang might have actually been a big bounce. Our universe may have been born from a previous universe that contracted, squeezed down to the smallest possible size, and then bounced back out, beginning the expansion we see today. In that moment of the bounce, time and space as we know them would have dissolved into a probabilistic cloud. This brings us to one last, profound mystery: the mystery of the arrow of time itself. Why does time seem to flow in only one direction? Why do we remember the past and not the future? The answer, surprisingly, has to do with heat. Think about it. A pendulum swinging without friction could swing forever, and if you filmed it and played it backward, the motion would still look perfectly natural. But as soon as you add friction, the pendulum heats its supports, loses energy, and slows down. That process produces heat. And you can instantly tell the difference between past and future. You will never see a stationary pendulum suddenly start swinging by absorbing heat from its surroundings. The difference between past and future only appears when heat is involved. The Austrian physicist Ludwig Boltzmann discovered why. Heat always flows from hotter things to colder things, not because of an absolute law, but because of probability. It's just statistically far more likely for a fast-moving molecule in a hot object to transfer some energy to a slow-moving one in a cold object than the other way around. The flow of time, the very distinction between past and future, is therefore rooted in chance. But it's also rooted in our own blurred vision. The arrow of time appears because we don't track every single molecule. We only interact with the world through a limited set of its properties: its temperature, its pressure, its shape. Our perception of time's flow emerges from this incomplete knowledge. For a hypothetical being who could see every quantum interaction in the universe, past, present, and future would all exist at once, a single, unified block. As Einstein once wrote to the sister of his lifelong friend after his death, people like us, who believe in physics, know that the distinction between past, present, and future is nothing more than a persistent, stubborn illusion. And this is where all three great mysteries converge: general relativity, quantum mechanics, and the nature of time and heat. And the key, the Rosetta Stone that might finally allow us to decipher them all, may come from the strangest objects in the universe: black holes. The great Stephen Hawking showed that if you apply quantum mechanics to the gravitational field of a black hole, you discover something incredible. Black holes are hot. They emit a faint heat, a thermal radiation. This is a quantum effect happening to a gravitational object, and it produces a thermal result. It is the first phenomenon we've ever found that involves all three pieces of the puzzle. It is there, at the edge of black holes, that we may finally begin to understand the true nature of time. Commentary. So, after this whirlwind tour of exploding universes, quantum leaps, and disappearing time, we have to return to the question that matters most: what about us? In this vast and glowing world, a swarming of ephemeral quanta and rippling space-time, what are we? If all of reality is just a great jigsaw puzzle of particles and fields, then where do our feelings, our dreams, our sense of self, come from. Carlo Rovelli ends his lessons by turning his gaze from the cosmos to ourselves, and what he offers is not a cold, sterile answer, but a deeply moving and human one. We are not external observers of this universe. We are an integral part of it. We are situated within it. We are made of the very same atoms, the same stardust, as the stars in the galaxies. For centuries, we have been on a journey of humbling discovery. We thought we were at the center of the universe, and we learned we are on a small planet in a remote corner of a vast ocean of galaxies. We thought we were a species apart from all others, and we learned we share ancestors with butterflies and trees. Like a child growing up, we are slowly learning that the world does not revolve around us. And in this process, in being mirrored by the vastness of reality, we begin to truly learn who we are. The world Rovelli describes is not at odds with our humanity, it is the very source of it. Our emotions, our values, our love, these are not less real for being part of nature. They are more real. They are the complex, beautiful form that nature has taken right here, in us. Even our sense of free will finds its place. To be free doesn't mean we can magically break the laws of physics. It means that our actions are determined by the laws of nature acting inside us, in the impossibly complex and fleeting interactions between the 100 billion neurons in our brain. When you make a decision, it truly is you who decides, because you are not some ghost in the machine. You are the machine. You are the whole, intricate, wondrous process. So, what can we take from these lessons today? Let me suggest 2 simple things. First, the next time you have a chance, go outside on a clear night and look up at the sky. Don't just see pinpricks of light. Try to feel the reality behind them. See the starlight that has traveled for millions of years to reach your eyes, its path bent by the curvature of space. Feel yourself on a spinning planet, flying through a universe that was born in fire and is still expanding. Connect with that sense of awe. Second, embrace your own curiosity. It is in our nature to want to know more, to learn, to explore. That drive is the same one that led Einstein to his revelations and Rovelli to his. It's the engine of science. Don't ever let anyone tell you that these big questions are not for you. They are for everyone. This small book is a testament to the power of that curiosity. It reminds us that science is not a dry collection of facts, it is a story. A grand adventure. It's the story of us trying to follow the tracks of reality, to understand our home a little better. And the most beautiful part of that story is that it is not finished. We are living on the edge of what we know, in contact with the vast ocean of the unknown. And it is there, at that boundary, where the mystery and the beauty of the world truly shine. And as Rovelli says in his final words, it's breathtaking. That was a summary of 7 brief lessons on physics by Carlo Rovelli. We certainly touched on the major ideas today, but I'll be honest with you, a summary can only ever be a map. The real magic happens when you walk the territory yourself. It's in the quiet moments, when Rovelli's elegant prose or a particular mind-bending idea connects with you in a way you didn't expect. This summary is designed to help you decide if this book is worth your time. If anything we've discussed today has sparked a sense of wonder in you, grab a copy. Reading it isn't just about learning, it's an experience that can genuinely change the way you see the world and your place in it. A link to the book is in the description. Also, if you found this journey valuable, please take a moment to click that like button and subscribe to the channel. It lets me know that these deep dives are helpful, and it ensures you won't miss our next exploration into another life-changing book. Let's keep learning together.